Okay, guys, hello, and we're back. I just wrote the recap of what we did on Wednesday, okay? Now, what we're working on is the trajectory of a particle under the influence of gravity acting downward and drag acting in the opposite direction of its motion, okay? Why am I doing this problem? This is not a problem that I would test you on, but this is a problem that I call like a symphony kind of problem, right? You know, you get tested on your scales, you get tested on your étude, for those of you who studied music. This is a problem that puts many things together, right? It has many steps to it, and I do have problems of this ilk on my test, which are multi-part problems, where you have to bring your understanding to this problem. And I wanted to convey an understanding of this problem because it's also experiential, I hope, for you, where you have some notion of what it means for a particle to fall, and you have some notion about air resistance, okay? And so let's see what the mathematics says about the things you may understand already, okay? Newton's law, A equals F over m. The velocity is the rate of change of position with respect to time. The acceleration is the rate of change of velocity with respect to time. So I'm just taking Newton's law, expressing it in terms of the velocity, and pointing out the velocity is the rate of change of position with respect to time. We imagine that a particle has a trajectory, so it has a position as a function of time, which we denote r of t. And r of t has components x, y, and z, each of which are functions of time. For shorthand's sake, you don't have to do this, but for shorthand's sake, I'm just going to write v as having its components. It's a function. It's three functions of time. It's a vector-valued function of time. It's u component, its I hat component of velocity, its j hat component of velocity, and its k hat component of velocity. Okay? U, v, and w. Simply put, u is dx dt, v is dy dt, and w is dz dt. You see, I didn't write everything down. Now, when I substitute the force of gravity onto the right-hand side of Newton's law and the drag force, as I discussed last time, this is the force that you have. This is the force that you're considering over here. Okay? One is gravity, the other one is drag. And I talked a bunch about the drag coefficient, how that depends on shape. It's an engineering thing. It's very important, and it's not this trivial, simple function, okay? But we're going to consider a linear drag. This is called linear drag, so it's proportional only to the velocity with a coefficient called the drag coefficient. And then when I substitute that into the right-hand side and divide by m, this is dv dt, and this is f divided by m. Of course, the m cancels in the gravitational term. That's the Galileo issue, okay? And then we are left with u, v, and w. That's the v velocity, divided by something, and I argued that that something has to be a time scale. It has to be a time. Why? Well, to balance the units on the right-hand side and the left-hand side, it must be a time. Because the left-hand side is velocity per unit time. This is an acceleration, which is velocity per unit time. And this is velocity, well, it better be per unit time. So I try to do this because I want you guys to think more deeply about your problems as you go forward. Knowing if you got meters on the right-hand side is an important way to make sure that you've written the right equation down, okay? Or meters per second squared. Okay, and then this time is just this combination, mass divided by the drag coefficient. And you see if the drag coefficient gets really, really huge, this time gets small. If the drag coefficient gets really, really, really small, this time coefficient gets huge. When this time coefficient is huge, that means for small drag coefficient, so it goes the ups and the downs, right? Huge tau, big denominator, small drag coefficient. It's almost like you can neglect this completely, because this is really, really big. So this is a really small term. And you really just have a particle under gravity. For a small time, a small time, which is a large drag coefficient, this is small, and the denominator is small means this term is more important. Okay? So that's how you can think of equations. That's how you stop and say, what is that equation telling me? Okay? Now, to get the system of equations we need to solve, I take the dot product of this equation with I hat. If I take the dot product of whatever you do to the left-hand side, you must do to the right-hand side. take the dot product with I hat. And the basis vectors are perpendicular to one another. I hat dot j hat is 0. I hat dot k hat is 0. Therefore, and I hat dot I hat is 1. It's a unit vector. So if you take the dot product with I hat on both sides, that side, all you're left with is du dt. And this side, all you're left with is negative u over tau. And that's the equation. That's one of the equations you get. You do that again with j hat, that's the second equation. You do that again with k hat, that's the third equation. You don't have to do this dot product, but that's really what it does is it interprets what you mean by a vector equation. A vector equation in 3 dimensions is really 3 regular equations, 3 scalar equations. Okay? And that's what you have over here. And so what are we going to do next? What am I about to do? I'm going to solve. I'm going to teach you ordinary differential equations, little baby or ODE. I'm going to solve for u of t. I'm going to solve for v of t. I'm going to solve for w of t. That's the first step. That'll tell me my velocity as a function of time. And you remember that the velocity is related to the tangent vector of the curve. Then I'm going to go back. I'm going to get these 3 guys, u, v, and w. Then I'm going to go back and substitute those into this equation here on the left-hand side. And then I'm going to get x, y, and z as a function of time. So I have to integrate again. Okay? So you're basically, I'm going to tell you, in this problem, you're basically doing 6 integrations. We're going to do 6 integrations. But they're not that big of a deal. They're actually kind of easy. There's only one that's challenging. Okay? There's only one integration that's challenging and novel. 6 integrations over here. Okay? So I did this whole explanation because there's going to be some technical work right now, okay? I'd like you to follow the technical work or not. Maybe you just let it wash over you and just pay attention to what I'm doing, okay? And maybe take some filler notes here and there. That way, you're not too busy writing down every detail and you're seeing the big picture. Because I really want you to see the big picture here more than anything else. Okay. So in general, the coefficient of drag is a function. Remember, I did that Taylor series expansion. I tried to tell you how awesome Taylor series is, right? The coefficient of drag is a function. It's a function of the shape of the object, but we're imagining a fixed shape object, so we're not going to allow that to vary. But it's also a function of the speed. At low speeds, the coefficient of drag is a constant. But as you get to faster and faster speeds, the coefficient of drag starts to jump up. It starts to do some crazy things. And that's what I said last time. There's a difference between going slowly, going really, really fast, and then hitting like the Mach 1, right? Going at the speed of sound. Okay? I apologize. I have a perpetual cold this quarter. If anybody has a Kleenex and wants to take pity on the professor, may I steal one from you, please? Yes.
So then why is it, if it's a function of velocity, then why is it being multiplied by velocity up there in the course?
It could be, well, I'm approximating it as constant right now.
Oh, okay.
I'm approximating it as constant. But I could make that a function of the magnitude of the velocity if we wish to do that. That would just make this problem ridiculously hard to solve. It starts to get much harder to solve, okay? And that's the problem that NASA deals with. When you launch a rocket into space, the drag coefficient, the drag coefficient is way different. It's not a nice linear function of velocity at those velocities, okay? Or when the shuttles were coming back, okay? That's a huge problem, okay? But we're just talking about a baseball. So let me just do a baseball. We'll do rockets tomorrow. It's not all rocket science. Okay, so that's the context for all this. Do as you wish. I've given you the advice on how to follow me in this course, in this derivation. Do as you wish now. I'm going to start solving these problems. I have to solve equation this, that, and the other thing, okay? Yes? Well, so why do I take the dot product? The point about taking the dot product is to interpret what I mean by a vector function of time equals another vector function of time. And what you mean by a vector function of time equals another vector function of time is that component by component, they are equal to each other. So I'm equating the I hat component on the left-hand side to the I hat component on the right-hand side, the J hat component on the left-hand side to the J hat component on the right-hand side, etc. Okay? If you want, plug your ears because this is going to get a little detailed. If you don't want to do this, like, why would you have to do this? Well, sometimes you don't have an orthogonal basis. Sometimes you don't have an orthogonal basis. Okay? We like to work in our orthogonal Cartesian bases, and for calculus, you'll be doing that. But you guys are growing up. You're going into engineering. You're going into other places, right? So I don't want you to just be restricted to the box of thinking that I provide for you, but I want to tell you that there are other ways to think. Okay? There are more generalizations of this. But I'm not going to do all of them. I can't. Or else I barely have half my class here today. I would have like even less than half. I appreciate that. I'm going to take the Kleenex. And this is for the sake of you guys, so you don't have to be grossed out. Thank you, sir. Okay. Let's solve this equation. By the way, look, if I can solve this equation, I can solve this equation, right? They're effectively the same equation. It's just with u replaced with v. So what am I going to do? That's a differential equation. I'm going to write du dt times 1 over u is equal to negative 1 over tau. The opposite of taking a derivative is taking an integral. Okay? So I'm going to take the integral of this equation. This left-hand side is a function of t. I don't know what it is as a function of t. Okay, I'm teaching you basic ODEs right now. This is sort of what happens in 22b. Pause. I do this with my kids, like a little pause. Come back over here, 1 second. The solution of u of t is going to be a function whose derivative is proportional to itself. You can actually solve this without what I'm about to do right now. Think about what function has a derivative that's proportional to itself. Okay? We're going to answer that question in a second. There's a hand over here. This right here? This is the coefficient of drag. That's CD right there. The drag coefficient. CD. That's a kind of capital C. I'm trying to make it a capital C. Okay? Okay. It's going to be the exponential. Okay. Don't tell anybody. We're going to figure it out. Okay, let's figure it out. I integrate both sides with respect to time. I'm integrating an unknown function with respect to time. So you should wrap your head around that. How is he going to do it? Watch and see. I have to integrate it, and I'm imagining that I'm going to start at a beginning time. Let's call that time t equals 0. Okay? And I'm going to end at a later time. I can't use little t because I'm going to integrate with respect to little t. It's a dummy variable. Let me use a fixed capital T to indicate that it's a different time. It's a time. It's a particular time. So I'm going to integrate from 0 to capital T. And so I take 1 over u du dt dt is equal to the integral from 0 to capital T dt. I see I'm multiplying both sides by dt and then integrating over tau. Now, the right-hand side is super, super easy. The right-hand side, yes, sir. Sure, I did. To see if you're paying attention, that was my test. Okay, the right-hand side is super easy. It's just, because tau is just some constant, the right-hand side is equal to negative capital T over tau. Okay? And the left-hand side I have to deal with. Okay? And I claim the right-hand side, the way you deal with the right-hand side, this is a dt, sorry, that's a really sloppy t. The way you deal with the right-hand side is you actually do a substitution. Can't call it a u substitution because it's got u in there already, okay? Let's just do a substitution. Okay? And since I know the substitution, I know the answer, but this is how this whole thing works, okay? You got to think, what substitution works here? Well, let me let s is equal to the natural logarithm of the absolute value of u of t. Okay? Why? When you take the differential of s, right, that's going to equal, now you got to use chain rule. Okay? And I just want to tell you that chain rule is a lot harder than you think it is. Or rather, you should spend some time digesting what chain rule means. Okay? I realize I have kids in my upper division class that I did some quick chain rule things, and they're like, what? I'm like, oh, we don't spend enough time thinking about what chain rule means. Okay? I can't go into all of that right now, but I want you to think about what chain rule means. So it's the derivative of this with respect to whatever times the whatever. Well, the whatever is time. I have to take the derivative of this with respect to time because this is a function of time. Okay? So how do I take the derivative of this with respect to time? Well, this is actually 3 applications of chain rule because it's a function of a function of, no, 2 applications. A function of time. Okay? So you take the derivative of the natural logarithm with respect to its argument and then evaluate it at its argument. The derivative of natural logarithm with respect to, if you have natural logarithm of f, the derivative of the natural logarithm with respect to f is 1 over f. The derivative of natural logarithm is reciprocal. So the derivative of natural logarithm here is 1 over u of t. Then you have to take the derivative of the inside with respect to t. Because this thing is a function of t, so it's going to be du dt. I don't know what that is, because I don't know what u of t is, and I don't know what du dt is. But I'm going to get rid of it. I'm kind of getting rid of it. And then this is a differential, so it's 1 over, so you get a dt over here. In other words, if I let s equal the natural logarithm of u, then ds is all of this stuff. And now you know why I chose s to be this natural logarithm. Because that substitution turns all of this into something really simple. And what it does, one second, what it does is it pushes my ignorance of u out of the integrand and into the endpoints of integration. My ignorance is going to go to the endpoints. And watch how it does that. Yes?
How come we don't just reduce dt over dt to 1? Are those not additional in the original interval?
So then you're going to, you cannot, that's not division, right?
Oh, okay.
Remember that although I've said a derivative is, subtraction and division, right? This act of doing this, which you will be doing in 21 or 22b at some point, is not correct. Because this thing is subtract, divide, and then take the limit. So to do this cancellation is a little sloppy. Okay? Now, in many cases, it effectively works. Okay? But you got to understand what you're really doing. And this is what you're really doing. You're not doing this truly. You're doing this set of substitutions here. And I ask you to challenge yourself to take your understanding to the next level. Don't do these operations willy-nilly just because somebody said you can do that. Understand that's why I've focused on the definitions so much. Because if you focus on the definitions, you can go through and understand what all of these steps really mean. And you're not high school students anymore, you're university students. That's what you're seeking in life.
Are there cases where that doesn't work? Like it turns out to be something completely different?
You have to be super careful if you got functions of multiple variables. You have to be super, super careful. It doesn't work in functions of multiple variables. So pretty much it almost always works. It always works in functions of one variable. Yes, it works in functions of one variable. But if I were to cancel that out, then look what happens. I'm going to have an aside, okay? What do you mean by that? Let's imagine we canceled the dt out. Shut your ears off if this starts to confuse you, okay? Just don't listen. If I were to cancel that dt out, then I have du over u evaluated at u equals 0 to u equals t. What's the problem with that? U is a velocity, right? So what I mean is u of t here. And so this thing that's why I was emphasizing that this is some unknown function of time that I'm integrating. It has to be integrated with respect to time because the units of this guy has to match the units of my dt. Because you're integrating with respect to this. So you're going from t is 0 to t equals, you're not going from u equals 0 to u equals t. You're going from t equals 0 to t equals capital T. U is a velocity. So you're going from u of 0 to u of capital T. So if you understand that, then you're cool. That's fine. If you understand that you mean u of 0 and u of capital T, then you're fine. But that's starting to confuse you already. I can see it in your faces. So don't do that. Right? Do things systematically. Okay? And that's what I'm saying. When you guys did u substitutions, the substitutions in 21b, this is what you're doing really. Okay? You're being careful. And to be careful over here means the following. I have let s be this variable. Okay? Now, when the point is I have to change, when you do a substitution s, you have to figure out what your s is in terms of your old variables. You have to figure out what your ds is, your differential is in terms of your old differentials. And you have to figure out what your boundaries of integration are. Okay? And so now you say when t equals 0, that's at the lower bound of integration. When t equals 0, s equals the natural logarithm of the absolute value of u evaluated at 0. Because all I'm doing is putting t equals 0 into this equation. Okay? When t equals capital T, which is the upper bound of integration, s is equal to the natural logarithm of the absolute value of u of capital T. If you can understand this, and I don't claim that you can understand it on the first go, but if you can understand this, you get a deeper understanding of what you do when you do substitutions. Okay? That's a when. Now I have all the tools to change my integral. So that whole interior part of the integral becomes ds. The lower bound of integration becomes the natural logarithm of the absolute value of u of 0. And the upper bound becomes the natural logarithm of the absolute value of u of t. And that's equal to negative capital T over tau for some particular capital T and some parameter, the drag time tau. This integral, don't look at the bounds of integration. The integral of ds is easy. It's just s. Derivative, underivative. Okay? And so this is s evaluated at the upper bound, which is the natural logarithm of the absolute value of u of t, minus s evaluate the lower bound, which is the natural logarithm of absolute value of u of 0, is equal to negative capital T divided by tau, which tells me, you use your rules, right? Natural logarithm of the difference of natural logarithms is the natural logarithm of the ratio. Take the exponential of both sides. A little bit of algebra. U of t is equal to u of 0 e to the minus capital T over tau. So it says, at a particular later time, your horizontal velocity was your original horizontal velocity times e to the minus amount of time that's transpired divided by the drag time. It's kind of cool. Okay? Notice that there's some unknown parameter here called the original velocity. The differential equations can't tell me how fast I threw that thing. I have to add that information. They can't tell me where I started to throw that thing. I have to add that information. So this is called an initial condition. To get the actual answer, you would need to say, you know, professor threw it that fast, and give me what that is. Okay? Well, if this is true for a particular later time, I didn't bias this in any way. I can change capital T to little t. And so what we have now is u of little t is equal to u, and I'm going to use a subscript just to avoid all the chalk. u0 e to the minus little t over tau. And by the way, what did I say? This equation and this equation are effectively the same equation. So if I were to replace u with v everywhere, I have v of little t is equal to v0 e to the minus t over tau. So I have an unknown velocity u0, unknown velocity v0, and that's just how fast I throw it in this direction, the component in this direction, and the component in that direction. Okay? I want to point out to you that as tau goes to infinity, right, when tau goes to infinity, that means c goes to 0. That means the drag coefficient goes to 0. This goes to like e to the minus 0, which is 1, which says that the horizontal velocity is unchanged. The horizontal, which is what you know. If you throw a ball, whoop, It's the vertical velocity that's affected, mostly, not the horizontal velocity. However, if you were to do the same thing underwater, right? That thing stops. Try it. Try to throw a ball underwater. Okay? Go into a deep pool and like push it. It goes. That thing stops pretty fast. Okay? And now you have a sense of what this tau means. Let's say tau was 5 seconds. Let's just say it was 5 seconds. After this thing has traveled for 5 seconds, 5 seconds divided 5 seconds is 1. Its horizontal velocity is equal to the original horizontal velocity times e to the minus 1, which is about a third. After 5 seconds it's gone to a third of its original speed. After 10 seconds, it's gone to a ninth of its original speed. After 15 seconds, 15 divided by 5 is 3. It's gone to about 1/27th of its original speed. So it's stopping. Okay? That's how you get these guys. Okay? By the way, I'm going to solve this next problem in lickety-split. Okay? Let me do this one lickety-split. Remember, u is the horizontal component, the x component, the I hat component of the velocity. So u, remember that u of t equals dx dt. U of t equals dx dt. You good with that? So let's write that out. That says dx dt is equal to u0 e to the minus t over tau. Now this is a very simple ordinary differential equation, because unlike that first equation, or any of those u, v, or w equations, they had my ignorance on the left-hand side and my ignorance on the right-hand side. My ignorance was on both sides. I had u on both sides. That's what I don't know. In this equation, I have my ignorance on the left-hand side, but I know what's on the right-hand side. I have an explicit function of time. So this is really easy to integrate, okay? And so let me write the integral down. The x of t minus x of 0, I'm just doing the integral of the left-hand side with respect to time. And I'm using the fundamental theorem of calculus, right? If you take the antiderivative of dx dt, it's x at the end time minus x at the beginning time. And that's equal to negative u0 times tau e to the minus t over tau. I just took the antiderivative of the right-hand side. The antiderivative of the exponential, I get the negative from the top and the tau from over here. And put differently, I have x of t equals its original x0, I'm going to use subscript again, minus u0, its original velocity, times tau e to the minus t over tau. And so this is a particle under a drag, its x velocity, its x position, okay? This is the x position of a particle under drag. So what does this look like, everybody? Let's just plot this, right? Let's imagine we had t over here, and we had x, which is a function of t on that axis. We're plotting x of t versus t. Well, we know at t equals 0. Did I get this right? Oh, no. People, professor made a mistake. Stop. I apologize. This is what happens when you try to be too compact with the board. I apologize. Please forgive me for this one. I saw what I thought might have been a mistake, and then I didn't really get it until the end. Let's do that again. Dx dt equals u0 e to the minus t over tau. Okay? I'm going to integrate both sides. Let's do the whole thing. From t equals 0 to t equals capital T of dx dt times dt. And that's equal to the integral from t equals 0 to t equals capital T of u0 e to the minus t over tau dt. It's just an antiderivative of both sides. Okay? the integral of the derivative is the function evaluated at x of 0. So x of t, capital T, minus x of 0. That's what you get here by a fundamental theorem of calculus. That's the fundamental theorem of calculus. This I actually have to do this function, and I'm left with negative u0 times tau times this function, e to the minus t over tau, evaluated at t equals 0, the lower bound, and t equals capital T, which is the upper bound. That's what we're doing. I forgot the t equals 0 in that one over there. And that's important. It's super, super important. So I got to get that. OK? So I'm going to bring that up and continue it over here. OK? So let's write it out. As I did before, I'm going to change capital T to little t, because I can get away with it. I'm going to use subscript 0 to talk about the initial position. And this is going to be equal to negative u0 times tau times e to the minus t over tau minus 1. Because when you evaluate t equals 0, that function evaluates to 1. You cool with that? This involves some thinking, right? This is a multi-step problem. So what does this function look like? Well, this is x, and that's t. And let me say that this is x0. That's x0, OK? At time t equals 0, look what happens. At time t equals 0, this is e to the power of 0, which is 1, minus 1. The whole thing is 0. So at time t equals 0, you're at x0, wherever you decide to start. So let's put x0 right over there. Take a look at, we've got an exponential and a constant here. Take a look at time t goes to infinity. It gets very, very large. Okay? When t gets very large, this exponential goes to 0. When it's several times tau, maybe even 5 times tau, right? E to the minus 5 is pretty small already. E to the minus 100 is ridiculously small. It's 100 times tau. This is really, really small. And this thing goes to x0 plus u0 tau. It goes to an asymptote. So if this is x0 plus u0 tau, this function goes like this. And what does that mean? It means if you throw a particle under drag, it slows it down enough that it eventually stops moving in the horizontal direction. It ends up at a certain distance later at u0 times tau. At a certain time later at u0 times tau. Well, at a certain time, as time goes to infinity, it goes to u0 times tau. Yes, sir? Why? OK, so I'm just taking a limit, right? So at t equals 0, this is 1 minus 1 is 0. So we're OK over there. The only thing I do is now just take the limit that t goes to infinity, right? The limit that t goes to infinity, this is exponential decrease, right? So this goes to 0. This function just becomes tiny, right? And so that the whole thing goes to x0 plus u0 tau. But you think about it, what you're doing is there's drag on this thing, right? And if there's drag, it's stopping it from moving. That was that exponential decay in velocity. The velocity decays exponentially, so the position must come to rest somewhere. Okay, and think of it throwing a ball underwater. Push it. It goes, it stops moving horizontally, and then it starts to sink. Okay? By the way, y of t satisfies this exact same equation with y0, v0. Done. So we got the horizontal motion of this whole thing. Okay? Now, let me, for the sake of argument, have some very simple initial conditions. Okay, I'm going to set the initial conditions right now. My initial condition is going to be where I start, x0, y0, z0. I'm going to call that the origin. Because you can always shift the origin to the start point, right? You can just measure my coordinates from me. Okay? So let x0 equal y0 equals z0. We haven't encountered these yet, but you would see where x0 comes into the y0 comes into the y of t equation, and z0 would also come into the z of t equation. Let them be equal to each other, and let them be equal to 0. I'm firing my ball from the origin. Okay? Now, up is up. Gravity tells me which way is down. The opposite of gravity tells me which way is up. I can't change up, right? But I can change my direction of my axis in the horizontal plane, right? I can measure x that way, or I could measure x that way. If I'm throwing my ball to you, I'm going to just call you in my x direction, and that's my y direction. Okay? In other words, I will choose my direction of motion because there is invariance, because there's horizontal symmetry. I will choose my direction of motion to be along one of the axes. Okay? And what that means is let v0 equals 0. This doesn't make it less general. It just means I've chosen the right coordinate system to make the algebra work out nice. Okay? And now, that tells me v of t, not the vector v, but the component is equal to 0. That tells me y of t is equal to 0. And that tells me x of t is equal to negative u0 tau, or maybe I'll rewrite it. I'll write it as u0 tau times 1 minus e to the minus t over tau. That's all I got. So I got 4 of these things integrated, and I got 2 more to go. And you can imagine that I left the last 2. It's my punchline. So are you guys with me? I'd wanted to get to length of curve today, but I really want you to see drag too. Okay, so I think it's pretty enough to see that it's worth your effort. Okay. So look, we've done a bunch of calculus here. We've done chain rule, we've done integration, we've done some graphical analysis. You know, we're putting a lot of things into this. We're thinking about curves in space, so we're going to ultimately get an R of t in all of this. I erased my equation for W, but I might remember it. Okay? So my equation for W was dW, the vertical velocity, the time derivative of the vertical velocity, dW dt, is equal to negative g. This is my fun one. Okay? This is my fun one. Minus W over tau. So there are many ways to do this, folks. Okay? What I want to point out is that there's a constant here. Okay? There's a constant right over here. And I'm going to rewrite this thing as follows. Negative W, that's this one, divided by tau minus W asterisk. Hate me. That's fine. You may hate me. What if I were to say that I'm going to, this is just a constant, g is just a constant, right? What is W asterisk? W asterisk, this special number, is equal to negative g tau. Okay? Negative g tau. How did I get that? Well, just recognize, distribute this negative. And so what you realize is W star divided by tau is negative g. So W star divided by tau is negative g. So W star is negative g tau. Okay? And you can say, why did he do that? Why did he do that? Okay? Well, I want to find W of t in all of this. And this is a little more complicated than the previous equation. But I'm going to make it super, super simple right now. Okay? Because I'm going to make one more substitution. Let us call it f. I'm going to define f as follows. I don't know W of t, but I'm going to say W of t minus W star is equal to another thing I don't know, f of t. Okay? I don't know f of t. I'm going to make this substitution. So the idea is to get rid of W and keep f in this equation. Okay. Well, you see on the right-hand side, that's pretty clear. I got negative f over tau. We good with that? Negative f over tau is what I have on the right-hand side. On the left-hand side, I need to calculate what dw dt is. Well, notice, if w minus w star is f, that means w of t equals w star plus f. That wasn't a hard manipulation. And if I take the time derivative of both sides, that says dw dt is equal to the time derivative of w star, but it's just a constant, right? It's g times a parameter. So that's 0, and so that dw dt is df dt. It's okay? I'm saying I don't know what w is. I have an equation for w, but I'm going to just shift that w by a constant and make an equation for f. So how do you get the equation for s? Well, I have to remove w everywhere. W is w star plus f, and I take its time derivative because I have to remove the time derivative of w everywhere. I got df dt. And so this equation says df dt equals negative f over tau. But I solved that one already. Right? That's the same equation that I had, well, wherever that u equation, in the v equation. I've transformed it to look like the u equation in the v equation. I moved that g term out of there. Okay? And so what's the solution to this equation? The solution to this equation is, if you recall, f of t is equal to some initial value f0 e to the minus t over tau. That was the solution, right? Before, when I had this with it was u of t equals u0 e to the minus t over tau. And now, this is just f of t equals f0 e to the minus t over tau. Okay? Now I go back, I'm like, okay, I got my f, but I really want my w. Okay? And so to get w, I just got to add w star to all of this. So w of t is equal to w star plus f0 e to the minus t over tau. So this has got a lot of things mixed up in it. And you should be like, what is he trying to say there? What's going on? I don't blame you if you have a little bit of like, where is this going in you? Okay? Okay. Now remember I said I need initial information. I need to know how much my vertical velocity, how big was my vertical velocity? Okay? And so how do I get that? I get that by saying, let w of 0 equal w at t equals 0. That is to say, evaluate this equation at time t equals 0, and I'm just going to call that the initial velocity. That's what that's the additional information I have to give. And you'll see this in ODE class. This is called applying initial data. It was easy before. It's a little more challenging because you've got to do a bit of algebra here. So w0, which is the left-hand side, is equal to w star plus f0, and then I'm going to let t equal 0. That means that's equal to 1. Well, that's not a super surprising result. That's not super surprising. And that means I can get rid of f0. That means f0 is equal to the initial velocity minus w star. Okay? So stay with me, everybody. Therefore, w of t is equal to this special velocity, w star, plus the initial velocity minus w star times the exponential e to the minus t over tau. Is that okay? W0 is the initial speed that I throw it up and down. W star is something that I haven't told you about yet. I've just kind of, well, I've told you it's that, okay? Now, what do we get? I'm going to plot w of t, everybody. Let's plot w of t. Let's imagine I throw this ball up. Okay? I throw this ball up. So w0 is going to be positive. So this is w of t versus t. I'm going to throw the ball up. It's going to be positive. What's going to happen here? At time t equals 0, look at time t equals 0, this is 1, right? And so W is W star plus W0 minus W star. So these guys cancel. So you got W0. So at time t equals 0, you're at W0. That's where you start. Your initial shot, up. I'm using it positive, okay? That's why it's like this. Now, as t goes to infinity, your asymptote question, as t goes to infinity, look what happens. This thing goes to 0 ridiculously fast. That means this whole term goes to 0. So you go to a value of velocity, which is W star. You asymptote to W star, and by definition, W star is negative because g is positive, it's 10 meters per second squared, and ta is positive. So this is a negative number. This is negative, this is W star, which is negative. And so it asymptotes to negative. So what happens is if I throw the ball up, it goes up, right? But it slows down and starts to decrease. Its velocity becomes more and more negative. At some point, its velocity becomes 0. That's at the top of its arc. And then it starts to go down. Well, you would say, hey, that should be, if you think of a parabola, like in regular gravity, this should be a line. This should be linear, right? The velocity goes up, and it comes down and becomes negative. But what happens is it turns around and goes to an asymptote. And this is called the terminal velocity. So W star is equal to the terminal velocity. So if you jump out of a plane, you start falling down, right? At some point, you do free fall, you're accelerating, you're going faster and faster and faster. Then at some point, the force of drag, boom, 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 that's my heart beating with excitement. Force of drag balances the gravitational force, and you cease to accelerate. And you are going at a certain velocity, and that's the terminal velocity. And that terminal velocity is equal to negative g tau. And if you guys want to remind me of what it was, negative g tau should be negative mg over c drag. Is that what I get? Right? So look at this. Look at this. Let's look at what the terminal velocity says. If the drag coefficient is huge, the terminal velocity is small. That's what you want, right? If you're jumping out of a plane, you want that terminal velocity to be as small as you can get it. So what happens with a parachutist? A parachutist cannot control her M, and she cannot control G. But she falls, and then she increases C rapidly. So she's falling for a while, enjoying the free fall, and out goes the parachute. Boom. And C gets really, really big. Okay? And of course, she doesn't immediately reach her terminal velocity. She's still accelerating because of that parachute, but then she will reach a terminal velocity. And ideally, that's small enough. Okay? But you see how it's related to the drag time. Okay? So that's how you get the velocity. And you can put parameters in here. Now I'm going to go one step farther. I'm going to go one step farther to get my z of t, right? What's my z of t in all of this? My z of t, again, dz dt is equal to w of t. And now I know my right-hand side, which is w star plus w0 minus w star e to the minus t over tau. So dz dt equals this. Now I just got to take the antiderivative of this, okay? And this is straightforward. And I'm going to apply the fact that z of 0 is z0. I'm going to start. Wherever I start is my 0 point, okay? Even if that plane's up in the atmosphere, high up in the atmosphere, that'll just be your 0 point. You start there. So you'll go to negative values of z. So take the antiderivative of both sides. That says z of t minus z0, but that's 0, is equal to w star times time, because you integrate a constant, it's just time, t there, minus, when you take the antiderivative of this, it's going to be negative tau w0 minus w star e to the minus t over tau minus 1. That e to the minus t over tau minus 1 persists. Okay? Now, it's a lot to see. It's definitely, I'm not going to tell you that it's a super, super simple expression. Okay? But see what happens here. Z of t, as t goes to infinity, this term goes to 0. This term over here You just get like a 1 here. You get some constant over here. But what happens is this, z of t, goes as w star times t. That means you're going at a constant speed pretty much with some additive constant from here as time goes to infinity. And w star is negative, so you're going down. Okay? So it took a long time to do the terminal velocity problem. And a little bit I've taught you 22b also. But part of teaching you this is to give you a reason for why you do all these curves and what the point about all this mathematics is. Okay? The last thing I would have liked to do, and it's a little harder, the last thing I would like to do, and I would like you to consider, this is, now we have a parametric expression, x of t and z of t. It's effectively in 2 dimensions in the xz plane. One thing to do would be, oh, how do I get z in terms of x? What does that curve z of x look like? Okay? And let me just tell you quickly what's going to happen. Where was my x? I lost my, there's my x over there. See this x over there? Okay? So you can eliminate, see that 1 minus exponential up there, right? And that appears over here too. So this thing right here looks like, with a negative here, this thing looks like x divided by Utah. Utah. This is x divided by Utah. So this is equal to w star times t plus w0 minus w star over u0, that's the u, the tau's cancel, and then I have some x there. And then I have to eliminate this t also. And you're going to get natural logarithms in there to do it. Okay? But I'm going to graph the curve because I know the answer. You should just do it. It's edifying. Okay? And just give me 30 more seconds, everybody. And the curve is this. And the best way to try to get experience with it is to really do it in a deep pool. If this is x now, and this is z now, and I remember I said everybody starts at the origin, I'm going to throw it up, and I'm going to go down. Because that natural logarithm happens, it's going to go like that. In the absence of drag, this thing would go like that. You don't get a